Motors, lights, power tools. These are all examples of devices that depend on electrical current to operate. More specifically, most of the electrical equipment used today operates on alternating current. As you probably know, there are two types of current: direct current, which is usually referred to as DC, and alternating current, or AC. The path that either type of current flows through is called a circuit. Here's a simplified illustration of an AC circuit. It consists of an AC power source, a conductor, and a resistor. This is a DC circuit. It also consists of a power source, a conductor, and a resistor. These two circuits look similar, and in some ways they are, but there's a big difference in how the power sources for these two circuits operate. In our DC circuit, the power source is a battery. Current flows from the negative terminal of the battery through the conductor, through the resistor, and back to the positive terminal of the battery. In a DC circuit, current always flows in one direction. Also, the negative terminal of a DC power source is always the negative terminal, and the positive terminal is always the positive terminal. A simpler way to say this is that a DC power source has fixed polarity. Power sources for AC circuits do not have fixed polarity. The polarity of an AC power source changes periodically. As the polarity of the power source changes, the direction of current flow changes too. Alternating current flows in one direction and then in the opposite direction. One way to provide power for an AC circuit is to use an AC generator. The generator produces the voltage that causes current to flow through the circuit. This is a simplified AC generator. It provides power for a circuit that includes a light bulb. The generator produces voltage by means of induction. To induce voltage, three things must be present: a conductor, a magnetic field, and relative motion between the conductor and the magnetic field. In this generator, this loop of wire is the conductor, and the magnetic field is provided by two permanent magnets. The relative motion comes when the conductor is rotated so that it cuts through the magnetic field. There are two more components in this generator: slip rings and brushes. The slip rings are on the ends of the conductor. They slide against the brushes as the conductor rotates. The current produced by the generated voltage flows through the brushes and then on through the circuit. The magnetic field between the magnet poles is made up of a number of lines of flux. As the conductor rotates, it cuts through the lines of flux. Because the conductor moves in a circular pattern, we can think of it as starting at 0 degrees and rotating through the 360 degrees that make up a circle. At 0 degrees, the conductor is not cutting across any of the lines of flux because the conductor isn't moving. Since there is no relative motion between the conductor and the magnetic field, no voltage is induced. As the conductor starts to rotate, this half cuts downward across the lines of flux, and this half cuts upward. To make it easier to follow what's happening, we'll focus on one half of the conductor, the half that's moving downward. Since the conductor is cutting across the lines of flux, there is relative motion and voltage is induced. As the conductor moves toward 90 degrees, the angle between the conductor and the lines of flux increases, and the induced voltage increases. Maximum voltage is induced at the instant that this half of the conductor reaches the 90-degree point. As the rotation continues towards 180 degrees, the angle between the conductor and the flux lines decreases, and the induced voltage decreases. When the conductor reaches 180 degrees, the conductor is moving almost parallel to the lines of flux, and no voltage is induced. At 180 degrees, the conductor is halfway through its rotation, and the polarity changes. The half of the conductor that was cutting downward across the lines of flux is now cutting upward, and the half that was cutting upward is now cutting downward. From 180 to 270 degrees, the angle between the conductor and the lines of flux again increases, and so does the induced voltage. At the instant that the conductor reaches 270 degrees, maximum voltage is induced. As the rotation continues from 270 degrees to 360 degrees, the induced voltage decreases because the angle between the conductor and the lines of flux decreases. When the conductor completes its rotation at 360 degrees, no voltage is induced because the conductor is again moving almost parallel to the lines of flux. This type of graph is called a sinusoidal curve or sine curve. You've probably heard it referred to most often as a sine wave. This sine wave represents the AC voltage induced as a conductor makes a complete rotation through a magnetic field. Let's see how this graph is plotted. The vertical axis of the graph represents the magnitude of the induced voltage. The horizontal axis represents the time that elapses as the voltage changes. If the plotted voltage value is above the horizontal line, it's positive. If the voltage value is below the horizontal line, it's negative. A voltage value that is on the horizontal line is neither positive nor negative. It's zero. Now, let's plot the voltage produced by the conductor in this simplified AC generator. We'll start with the conductor in the vertical position. When it starts to move, the movement will be almost parallel to the lines of flux that make up the magnetic field. At this starting point, the angle between the conductor and the flux lines is 0 degrees, and no voltage is induced. When the conductor starts to rotate, it begins cutting across the lines of flux, and voltage is induced. As the conductor rotates to the 90-degree position, the angle increases, and so does the magnitude or value of the induced voltage. At 90 degrees, the conductor is moving perpendicular to the flux lines, and voltage is at its maximum positive value. As the conductor rotates toward 180 degrees, the voltage decreases because the angle between the conductor and the flux lines decreases. At 180 degrees, the conductor is moving parallel to the flux lines, so the value of the induced voltage is again 0. At this point, the polarity changes. As the conductor moves from 180 degrees to 270 degrees, it cuts through the flux lines in the opposite direction, and the voltage starts to increase in the negative direction. The voltage reaches its maximum negative value when the conductor is at the 270-degree point. The voltage then decreases again until, at 360 degrees, it's back at 0. The voltage that's produced by this generator will cause current to flow if there's a complete circuit to provide a path for it. This complete circuit has a light bulb for the current to flow through. Slip rings and brushes connect the conductor to the circuit. Now, as the conductor rotates, we'll plot a graph again, but this time we'll have two sine waves, one for voltage and one for current. As the conductor turns, the voltage and current build up to their maximum positive values and then decrease to 0. Then both voltage and current reverse direction and build up to their maximum negative values. When they decrease to 0 again, they'll have completed one cycle. In this case, what we mean by one cycle is one full rotation of the conductor through 360 degrees. A cycle is also one complete sine wave. During each cycle, the current flowing through the light bulb causes it to brighten, dim, go out, brighten, dim, and go out again. In a typical AC power system, 60 cycles are completed every second. The number of cycles completed each second is called frequency. Frequency is measured in units called hertz. 60 cycles per second can therefore be referred to as 60 hertz. This graph shows one cycle of a typical AC voltage sine wave. In this part, we're going to take a closer look at some specific points on this graph. Although we'll be referring to voltage, the terms we'll use apply to AC current as well. We'll start with this point. This point represents the voltage's maximum positive value. And this point represents the voltage's maximum negative value. The voltage values at these 2 points are referred to as peak values. Each cycle has one positive peak and one negative peak. The amount of voltage represented by the distance between the positive peak and the negative peak is called the peak-to-peak value. Now, even though it may be handy to know about peak values and peak-to-peak values, these values aren't commonly used when you're working with AC circuits and equipment. Alternating current doesn't build up to a peak and then stay there like direct current does. So most of the time, when we're dealing with AC, we talk about effective values. Effective values are based on a comparison between AC current and DC current. To make this comparison, scientists did a lot of experiments to measure the heating effects of AC and DC current. From their experiments, the scientists discovered that 1 ampere peak value of alternating current produces the same heating effect as 0.707 amperes of direct current. In other words, effective AC values are equal to peak values times 0.707. This relationship applies to both voltage and current because voltage produces current. Effective values for AC are often called RMS values. The letters stand for root, mean, square, which refers to the mathematical formula that's used to determine effective values. RMS values provide a way to compare AC voltage and current, which vary over time, with DC voltage and current, which do not vary over time. Some devices, such as heaters and light bulbs, can be used in either AC circuits or DC circuits. The voltage and current ratings on these devices are DC values and AC RMS values, which are the same. In this topic, we looked at alternating current. We saw how it's different from direct current, and we saw how the voltage and current produced by an AC generator can be plotted on a graph as sine waves. We also discussed peak values, peak-to-peak values, and effective values. Now spend some time answering a few practice questions to check your understanding of alternating current. Inductance is a physical property of all circuits that opposes changes in current flow. It's measured in units called henries. When we talk about the effects of inductance, we generally use another term, inductive reactance. Inductive reactance is the measure of the opposition to current flow that's created by inductance. Because inductive reactance, like resistance, limits current flow, it's measured in ohms. To understand how inductive reactance limits current flow, it's first necessary to understand a process called self-induction. Self-induction is the induction of voltage in a conductor by AC current flowing through that conductor. This cross-sectional view of a conductor can help us understand how self-induction works. When voltage is applied to the conductor, current starts flowing through it. The current flow causes a magnetic field to build up around the conductor. The magnetic field that builds up starts at the center of the conductor and moves outward. The magnetic field continues to expand until the current that is producing it reaches its peak value. Now, while the magnetic field is building up, there is relative motion between it and the conductor because the field itself is moving. Whenever there is relative motion between a magnetic field and a conductor, voltage is induced. In this case, a current-carrying conductor is inducing voltage in itself, so we call the process self-induction. As the magnetic field builds up, the voltage induced in the conductor is opposite in polarity to the applied voltage. This induced voltage can be called countervoltage, counter-electromotive force, or more simply, CEMF. Because it opposes the applied voltage, the CEMF limits current. After the current flowing through the conductor reaches its peak positive value, it decreases until it reaches zero. As current flow decreases, the magnetic field collapses. The motion of the magnetic field collapsing is opposite to the motion of the field building up. Since the motion is opposite, the self-induction is also opposite. The voltage that's induced in the conductor now has the same polarity as the applied voltage. When the magnetic field has collapsed completely, there is no motion, so there is no self-induction. Then, as current flow starts to increase toward its peak negative value, the magnetic field builds up again. Whenever there's a change in current, the magnetic field also changes. The voltage that's induced in the conductor is always in the direction that opposes the change in current. In other words, if the current is trying to increase, the induced voltage opposes the applied voltage and opposes the change in current. If current is trying to decrease, the induced voltage aids the applied voltage and opposes the change in current. There are several factors that affect the amount of inductive reactance. That is, the amount that current flow is limited by inductance in a circuit. For instance, there is a relationship between the strength of the magnetic field cutting across the conductor in a circuit and the amount of inductive reactance in the circuit. So, anything that increases the strength of the magnetic field cutting across the conductor increases the inductive reactance. And anything that decreases the strength of the magnetic field cutting across the conductor decreases the inductive reactance. Let's see how inductive reactance can be increased by coiling a conductor. Here's a conductor that's wound into a coil. It provides more inductive reactance than this straight conductor. A straight conductor is cut only once by its magnetic field when the magnetic field changes. But with a coil, as you can see, the magnetic field developed by each turn cuts across almost every other turn as the magnetic field builds up and collapses. The more turns there are in the coil, the higher the inductive reactance will be. The inductive reactance that a coil provides can be further increased by placing an iron core inside the coil. The iron core concentrates and directs the magnetic field that the coil produces. So, inductive reactance can be increased by coiling a conductor and adding an iron core. Now, because inductive reactance limits current, when you change the inductive reactance, you are also changing current. Increasing the inductive reactance decreases current, and decreasing the inductive reactance increases current. Inductive reactance is a measure of the current-limiting effects of inductance in a circuit. In this part, we're going to examine the relationship between inductance, current, and voltage. This is a sine wave that represents the voltage induced as a conductor rotates through a magnetic field. Here's the circuit that produces the sine wave. The amount of inductance in this circuit is so small that for our purposes it's insignificant. So we'll say that the only current limiting factor in this circuit right now is the light bulb that provides resistance to current flow. This type of circuit can be referred to as a purely resistive circuit. In a purely resistive circuit, as long as the resistance remains constant, when voltage increases, current also increases. When voltage decreases, current decreases. When voltage and current stay together in this manner, they're said to be in phase. Now let's look at a purely inductive circuit. That's a circuit in which inductance is the only factor that limits current. Now actually, this type of circuit only exists in theory, because all circuits have some resistance. But it's helpful in understanding the effects of inductance on the relationship between voltage and current. In this purely inductive circuit, when voltage starts to increase, current does not increase right away. That's because the current flow is limited by an induced voltage that opposes the applied voltage. This induced voltage, which is commonly referred to as counter-electromotive force, or CEMF, keeps the current from increasing immediately. Therefore, the increase in current takes place later than the increase in voltage. When voltage starts to decrease, the induced voltage opposes a decrease in current. So the decrease in current takes place later than the decrease in voltage. Because the changes in current always take place later than the changes in voltage, it can be said that current lags behind voltage during the entire cycle. Whenever voltage and current increase and decrease at different times, they are said to be out of phase. In our purely inductive circuit, inductance causes voltage and current to be out of phase. In this topic, we looked at inductance. We saw how inductance limits current flow in AC circuits, and we discussed inductive reactance. We also examined some factors that affect inductive reactance and the relationship between inductance, current, and voltage. Now would be a good time to answer some practice questions to be sure you understand the material we've covered. Capacitance is a physical property of all circuits that opposes changes in voltage. It's measured in units called farads. Capacitive reactance is the measure of the opposition to current flow that is created by capacitance. Capacitive reactance, like inductive reactance and resistance, is measured in ohms. Capacitance is often added to circuits in power systems to counter the effects of inductance. Inductance is a physical property of all circuits that opposes changes in current. When the inductance in a circuit would limit current flow more than a desirable amount, additional capacitance can be added to the circuit to bring current flow up to the level that's needed. The devices that are used to add capacitance to electrical circuits are called capacitors. A capacitor is a device that stores energy. This is a simplified illustration of a typical capacitor. It's made up of two plates separated by an insulator. The insulator is called a dielectric. Its purpose is to keep the flow of electrons or current from moving from one plate of the capacitor to the other. The dielectric can be made of any good insulating material, including air. Now, before a capacitor can store energy, it has to have energy supplied to it. The process of supplying energy to a capacitor is called charging the capacitor. Let's see how it's done. To begin with, the capacitor's plates are electrically neutral. Each plate contains both positive and negative charges. When the capacitor is connected to a power source and the power source is turned on, electrons flow onto one of the capacitor's plates. Because the plates are separated by the dielectric, current does not flow through the capacitor. Because the dielectric blocks the flow of electrons, the first plate has an excess of electrons. Since electrons are negatively charged, the plate has a negative charge. Because like charges repel each other, the negative charge on the first plate forces electrons away from the second plate. The second plate thus becomes positively charged. The electrons that are forced away from the positive plate flow back to the power source. The flow of electrons from the power source to the negative plate and from the positive plate back to the power source continues until the peak voltage is reached. When the peak voltage is reached, the negative plate has gained a certain number of electrons, and the positive plate has lost the same number of electrons. For any given voltage, it takes a specific number of electrons to fill the negative plate. That number is called the capacity of the capacitor, or simply the capacitance. If too much voltage is supplied to a capacitor, too many electrons will be forced onto the negative plate. As a result, the dielectric material could break down. If that happens, current could flow through the capacitor from one plate to the other. In most cases, current flowing through a capacitor will destroy the capacitor. Now try a question to be sure you have an understanding of capacitance. Capacitive reactance is a measure of the opposition to current flow that is created by capacitance. In this part, we're going to examine the relationship that exists between capacitance, current, and voltage. This circuit contains an AC power source and a capacitor. When power is supplied, electrons accumulate on one plate of the capacitor, and electrons are forced away from the other plate. Each electron that's added to the first plate makes that plate more negative, and each electron that leaves the other plate makes that plate more positive. As a result, a difference in potential develops across the capacitor's two plates. A difference in potential is voltage. So what happens is that a voltage builds up across the capacitor as the capacitor is charged. This voltage opposes the source voltage. We can use a sine wave graph to better understand the relationship between capacitance, current, and voltage. Keep in mind, as we look at the sine waves, that we are assuming a purely capacitive circuit. That is, a circuit that is not affected by resistance and inductance. The sine waves represent the source voltage and the current that's produced during a full AC cycle. At the beginning of the cycle, as the source voltage starts to rise from zero to its maximum positive value, current flow is maximum in the positive direction. As the source voltage rises, the capacitor is being charged, and the voltage across the capacitor is building up. At the moment when the capacitor is fully charged, the source voltage is at its peak positive value. The voltage across the capacitor is equal to the source voltage, but it opposes the source voltage. The two voltages have the effect of canceling each other out, so there is no current flow. Current is at zero. When the source voltage passes its positive peak, the capacitor starts to discharge. Discharging is the reverse of charging. Electrons leave the negatively charged plate and flow onto the positively charged plate. current flow reverses direction. When the source voltage reaches zero, current is at its peak negative value. As the source voltage increases from zero to its peak negative value, the capacitor is being charged, but in the opposite direction. When the source voltage reaches its peak negative value, the capacitor is fully charged. Again, the source voltage and the voltage across the capacitor are equal and opposing, so current is zero. As the source voltage passes its negative peak, the capacitor again starts to discharge. When the source voltage reaches zero again, current is at its peak positive value, and the cycle is complete. Now, in the example we just looked at, capacitance was the only factor that affected current and voltage. In a purely capacitive circuit, capacitance causes voltage and current to be out of phase. Because capacitance opposes a change in voltage, changes in current always take place ahead of changes in voltage. Another way to say this is that in a purely capacitive circuit, current leads voltage by 90 degrees. Now see if you can answer a question about the relationship between capacitance, current, and voltage. In this topic, we discuss capacitance. We learn that capacitance is a physical property of all circuits that opposes changes in voltage, and that capacitive reactance is the measure of the opposition to current flow that's created by capacitance. We also discussed the relationship between capacitance, current, and voltage. We'll stop here and give you an opportunity to check your understanding of capacitance. In an AC circuit, there are three different kinds of power: true power, reactive power, and apparent power. True power in an AC circuit is power that is actually used to do work. The power in a purely resistive circuit is true power. These sine waves represent voltage and current for a purely resistive AC circuit. In a purely resistive circuit, voltage and current are in phase. They always increase and decrease in the same direction at the same instant. We can use these voltage and current sine waves to determine the true power in the circuit at any instant. All we have to do is multiply the voltage at any instant by the current at that same instant. Since voltage and current are in phase, they are positive at the same time and negative at the same time. Therefore, their product, true power, will always be positive. Whenever you multiply either two positive numbers or two negative numbers, you get a positive product. Now, the term positive power is just a convention. When we talk about positive power, we mean power that's going from a power supply to a load. When we talk about negative power, we mean power that is returning to a power supply from a load. We can better understand what this means by looking at a second type of AC power, reactive power. Reactive power is the type of power found in a purely inductive circuit or a purely capacitive circuit. It represents the amount of energy that is temporarily stored in a reactive device, such as an inductor or a capacitor. Reactive power is often defined as power that does not do any useful work. These sine waves represent voltage, current, and reactive power in a purely inductive circuit. Voltage and current are out of phase, with current lagging behind voltage. In the first quarter of the AC cycle that these sine waves represent, voltage is positive and current is negative. Multiplying the two together gives us negative power, because the product of a positive number and negative number is a negative number. During the second quarter of the cycle, voltage and current are both positive, so their product is positive. The same relationships can be seen during the second half of the cycle. In the third quarter, when voltage becomes negative, current is still positive, so power is negative again. Finally, during the last quarter of the cycle, both voltage and current are negative, so power is positive. In a purely inductive circuit, positive power goes from the power supply to the inductive device. The inductive device absorbs the power as its magnetic field builds up. During the negative power periods, the power absorbed by the inductive device returns to the power source as the magnetic field collapses. The amount of power that's returned from the inductive device to the power source is equal to the amount of power that's supplied by the power source to the inductive device. So in a purely inductive circuit, power just goes back and forth between the power source and the inductive device. No power is used to do work, so there's no power that we can identify as true power. The power in a purely inductive circuit is only reactive power. In a purely capacitive circuit, when power is positive, the capacitor is charging and storing up power. When power is negative, the capacitor is discharging and returning power to the power source. The effect is the same that we saw for the purely inductive circuit. The amount of power that's returned from the capacitor to the power source is equal to the amount of power that's supplied by the power source to the capacitor. Again, the power doesn't do any work, so it's reactive power rather than true power. The last kind of AC power is apparent power. Apparent power is the power used to do work and the power stored during part of a cycle by inductive and capacitive devices and then returned to the power source. To calculate apparent power for any circuit, you just multiply voltage times current. This AC circuit contains an AC power source and a resistor. With these components, the circuit is a purely resistive circuit. In a purely resistive circuit, true power and apparent power are equal. The value is obtained by multiplying voltage times current. When we add an inductor and a capacitor to the circuit, we no longer have a purely resistive circuit. If we multiply voltage and current together for this circuit, we won't get true power, because true power is calculated this way only for purely resistive circuits. We also won't get reactive power, because there is a resistor in the circuit. The product of voltage times current for this circuit is apparent power. In a circuit like this one, we have to consider the effects of resistance, inductance, and capacitance. Taken together, the combined effects of all three factors on current flow, and therefore on power, are called impedance. Impedance can be calculated, but you're not likely to have to do it. In most cases, the true power in an AC circuit that is affected by impedance is calculated using the power factor for the specific circuit. The power factor is the ratio of true power to apparent power in an AC circuit, and it's usually expressed as a decimal value. Any time that you know the apparent power in a circuit and the power factor for that circuit, you can multiply the apparent power times the power factor to find the true power. Another way to say this is that voltage times current times power factor equals true power. The two common types of AC power systems are single-phase systems and three-phase systems. In this part, we're going to examine some basic concepts associated with each type. Single-phase systems are the most commonly used AC power systems for general electrical needs. There are two basic types of single-phase systems: two-wire systems and three-wire systems. This illustration represents a simplified two-wire system consisting of two wires, a voltage source, and a load, which is a resistor. In a two-wire system, the voltage supplied can have only one value. Since it's often desirable to have more than one voltage, the three-wire single-phase system was developed. The three-wire system makes it possible to have two different voltages from one voltage source. The component that changes a two-wire single-phase system to a three-wire single-phase system is a transformer. As this illustration shows, two lines come into the primary side of the transformer, and three lines come off the secondary side. The middle line on the secondary side is called the neutral line. It divides the secondary into two halves. The voltage between the neutral line and either the top line or the bottom line is 120 volts. The voltage between the top line and the bottom line is 240 volts. So it is possible to get either 120 volts or 240 volts from this three-wire single-phase system. The neutral line in a three-wire system is usually grounded as a protective measure. The same is usually true for one of the lines in a two-wire system. Then, if an ungrounded line accidentally becomes grounded, a short circuit will occur, and the circuit's fuses or circuit breakers will open the circuit. Although single-phase AC systems have a wide range of uses, the systems that are used most often when large amounts of electric power are required are three-phase systems. Three-phase AC systems are found in most industrial installations. The two types of connections that are commonly used for power sources and loads in these systems are delta connections and Y connections. This is a delta connection. The triangular shapes are similar to the shape of the Greek letter delta. In this illustration of a delta connection, the three coils represent a three-phase transformer. The ends of each coil are connected to the ends of the other two coils. The three wires coming out of the transformer are connected to three resistors, which are also delta connected. It's important to note that the current and voltage in the coils and the resistors of a three-phase system are not always the same as the current and voltage in the wires. The current that flows through the coils or the resistors is called phase current. The voltage that's applied across the resistors or induced in the coils is called phase voltage. The current that flows through the wires is called line current, and the voltage that's applied to the wires is called line voltage. In a delta-connected system, the phase voltage equals the line voltage, but the phase current does not equal the line current. Each coil or resistor is connected across two wires, so the voltage in each coil or resistor is equal to the voltage in those wires. However, the ends of two coils or two resistors are connected to one wire, so the current flow through the coils or resistors is not equal to the current flow through the wires. The line current is actually equal to the phase current times the square root of 3. Since the square root of 3 is 1.73, we can say that the phase current times 1.73 equals the line current. You'll need to know this when you're taking readings of current and voltage on three-phase systems that are delta connected. The other common type of connection for three-phase systems is the Y or star connection. In a Y connection, one end of each coil or resistor is connected to one end of both of the other coils or resistors. The free ends of the coils or resistors are connected to the three phase lines. In a Y-connected system, the phase current is equal to the line current, but the phase voltage is not equal to the line voltage. The phase current is equal to the line current because the current flowing through each line has to flow through the coil or resistor in the line. The phase voltage is not equal to the line voltage because the voltage in each coil or resistor has to be added to the voltage in one of the other coils or resistors to form the voltage across any two wires. In Y-connected systems, line voltage equals phase voltage times 1.73. Now try a question to check your understanding of the material we just covered.